Everyone, welcome back. Today we'll look at the second lecture in the series, which is EM02. So we'll move on from Maxwell's equations now. Today we're going to do boundary conditions. And constitutive relations. So we'll do some constitutive relations today, and then in the next lecture we'll continue it. So let's get started. So we'll start maybe with boundary conditions. Okay, so in the last video, we looked at Maxwell's equations in differential and integral form, and we said basically they relate, the four different fields, the E, H, D, and B fields, with the sources, which are the current density and the charge density. But strictly speaking, the point form of Maxwell's equations are only valid at a point where the neighborhood is homogeneous, or there are no singularities in terms of not necessarily singularities, but no discontinuities, I would say, because you really need the neighborhood at that point to be continuous in order to be able to take the derivatives, right? The curl gradient and so on and so forth. So in cases where you do have a material discontinuity, so let's say you have one material here and then up here there is another material. So how do you deal with that? You can't really take um, gradients and derivatives, for example, curl and divergence at this interface. So to deal with that, we introduce boundary conditions. Okay, so today we'll kind of derive how these boundary conditions turn out to be from Maxwell's equations itself. Okay, so this is the geometry that we have. We have two media, and we create essentially a cylinder that half of it is in the bottom medium and half of it is in the top medium. Okay, so maybe the top medium part of the cylinder looks something like this. And then the bottom is in the other medium. And then this is the construction that we're going to start with. Well, the top plate or the top disc of the cylinder has a normal N1 hat, and the bottom one has a normal N2 hat. Okay. I'll say that the area of this top surface is, let's just call it S. The total volume of the cylinder is V, and the length of the cylinder is delta L. Okay, so that's the construction. And now we'll start with Maxwell's equations. So we have Faraday's law, says minus dB t. And what I'll do is I'm going to integrate on both sides with over this volume of the cylinder. Okay, so what does that give us? That gives us the volume integral, the curl of E dV. And there is an identity which we discussed in the first video, the EM00 video, which is the sort of the 3D version of Stokes' theorem. If you apply that, you get E cross ds. But on the right hand side is still the volume integral over minus dV over dt dV. Okay. So now we take the limit as delta L goes to 0, which is the same thing as saying the volume goes to 0. It's not exactly the same thing. Delta L going to 0 makes volume going to 0, but you can also send the volume to 0 by taking the disk and making the radius of the cylinder 0. Right? But this is the way we're taking it to 0, is we're taking delta L to 0. Okay, so when we do this, it's a little bit, we have to do this a little bit carefully. So this is a field quantity, right? dB over dt. So we know that the fields satisfy Maxwell's equations, which means that they don't have any singularities, right? Because you do take derivatives. So for example, if B had some kind of a singularity, then the current would have to be infinite because of Ampere's law. Right? So because fields don't have any singularities, they are continuous in space inside this volume. Because they are continuous inside this volume, this integral goes to zero. As the volume goes to zero, the field doesn't go to zero, but the integral itself goes to zero because the volume of that integral is zero. Or volume of the cylinder goes to zero. Right? So the right hand side basically goes to zero. Again, that's only because there are no singularities in this quantity. And we need to be a bit careful about that because we'll see in the next case that doesn't happen. Okay, so the right hand side goes to zero, which means that this surface integral E cross ds is zero. Right, so what is the surface integral? When you take the limit, it's nothing but just the top surface and the bottom surface, right? So that is E cross n1 hat plus, there will be two different electric fields, the electric field on the top, in the top region and the bottom region. So it's E1 cross n1 hat plus E2 cross n2 hat times ds. And we have a surface integral over the two surfaces basically. Right? And since these surfaces are arbitrary and the entire integral goes to zero for any surface, it must be true at every point. And because of that, we can say that E1 cross n1 hat plus E2 cross n2 hat is equal to zero. But since n1 and n2 are pointing in the opposite directions, we can, and when this delta L goes to zero, they become basically the same disk. Right? So we can write n1 hat would then just be nothing but minus n2 hat, which we can call as n hat. Right? So, which means that you have nothing but n hat cross E1 minus E2 equal to zero. That's the first boundary condition. So what does this boundary condition really mean? Let's do that. So if I have this surface, some surface like that, at every point there is a normal component going that way in hat. And if there's some electric field, let's say on this side of the surface there's an electric field like that, which is E1. And on this side of the surface, the electric field is like this, let's say, and that's E2. When you calculate n hat cross E1, that gives you nothing but the tangential component of this electric field. And when you do n hat cross E2, that also gives you the tangential component of this electric field, right? Because of course you can break up this electric field into a tangential component and a normal component, and n hat cross the normal component is zero because they're in the same direction. That's the property of the cross product. Whereas the n hat cross the tangential component is non-zero, right? So you get a large tangential component. You only have the tangential component essentially. So this is just saying that the electric field across any boundary has to have a continuous tangential component. So the tangential component of the electric field is continuous across any boundary. Okay, that's what the boundary condition is saying. So let's actually write that down. Tangential E must be continuous. Okay. So we can play the same trick with Beer's law next. Take volume integral curl of H EV is H cross ds, which is now the right hand side, is the volume integral over dd over dt dv plus the volume integral over jdv, right? And by the same argument, this term goes to zero. But we need to be careful about this. Okay, so if this current density is indeed volumetric, which means it is sort of distributed in volume, as we defined earlier, then this integral also goes to zero. Right? Which means if J is sort of finite everywhere, then this goes to zero. But sometimes what can happen is that at this boundary, let's say that's the boundary, you only have a current that's flowing confined to this boundary, J. So J is not flowing in the volume, right? So a volumetric current would flow kind of everywhere, right? So you can think of J as flowing only on the surface of a plane and not in the volume, right? So this can be kind of confusing the first time if you're seeing this, but if we define it, maybe that helps, right? So we define J. So what was J? So I said J was if some current is flowing in some volume, take a small patch, just to remind you, right? So we had, let's say a current was flowing like that in some volume of space. At a single point, we said we can take the tangential component of these flow lines, place a small patch that's normal to that tangent, and then calculate how much current is flowing through this patch, right? Okay, but then if it's flowing on a surface, what do you do? So then what you do is, so let's say this is the surface. I'm looking at it from above. I have these currents that are flowing on this surface, right? So then what you can do is you can place a small line now, this line, and I'll say there is a normal component to this line. Right? So you pick a point of the flow line, you place a line across it, and then you see how much current is flowing through this line. If this line has some length delta L, then J surface current density would be amount of current flowing through delta L along this n hat. Okay, so there is a relationship between J. So just to remind you, this is amount of current flowing through a surface dot n hat, right? A small surface element, whereas Js is through a small line element. Okay, so how do you actually relate the two of them? So I can write J. So J is a function of x, y, z. Every point in space, right? Because it's flowing through a volume, you can pick a single point, you can see which direction at that point the current is flowing, put a normal there, make a surface perpendicular to that normal, and then see how much current is flowing through that. But Js in this case, we'll just take an example of Cartesian coordinates, would only be flowing on the surface. So it's only a function of x and y. So what is the function in z then? So in z, it's a delta function, which is a Dirac delta function. Hopefully you've seen that before. Dirac delta function is basically zero everywhere, and at z equal to zero, it's some undefined value, such that when I take the integral minus infinity to infinity, delta of dz of z is equal to 1, right? So in fact, the delta of z has units of 1 over meters, right? Because this integral goes to 1, and this has a unit meters. So this must have 1 over meter, right? So that comes out to be 1. It's unitless. The integral should be unitless. Okay, so the same thing is here. So here we have the unit is ampere per meter square. This one's unit is only ampere per meter, as you can see from here. And you have one more 1 over meter from this. So on the right-hand side also you have ampere per meter square. Okay, which means that actually now, if you look at J, this is in fact singular, right? Because of this singularity. There is a singularity in C. Of course, this doesn't have a singularity because it is in fact a limiting quantity, but this delta of Z is a singularity in Z, right? So that's why that integral we need to treat very carefully. So let's go back and look at this, revisit this integral now. So what happens to this integral? So just as an example, we can do it in Cartesian coordinates. X bar c j dx dy dz. J is not a function of z, so you have nothing but xy, j of x comma y, volume integral, the z integral of delta of dz dx dy. Right, but what is this? This is nothing but, maybe I should say, this is nothing but 1, right? So that means this has been reduced to xy, js, I'll call it, dx dy. Okay. And in a generalized coordinate system, it would be a surface integral js ds. So this integral, in fact, does not go to 0. It's important to understand why that doesn't go to 0 and why the fields do go to 0, right? Because in fact, the currents and the charge densities that we have are something that we define, right? So we can define them to have certain singularities, whereas the field quantities come from Maxwell's equation, so they do have to obey continuity, so they cannot be singular. So that's kind of an argument as to why this integral doesn't go to 0 or need not go to 0. Right, so putting things together, that gives us, so we have surface integral n1 hat cross h1 n2 hat cross h2 ds, similar to earlier, is nothing but surface integral of js ds. And again, we can say since s is arbitrary, it has to be true at every point, which means that we have n hat cross h1 minus h2 is equal to js. The magnetic field follows a slightly different boundary condition. So what is this boundary condition saying? So this boundary condition is saying if I have a magnetic field that the tangential component, since you know that now n hat cross means it's a tangential component on one side, and on the other side, the other material I have a tangential component that's a little bit different, then there has to be a surface current flowing at this interface. Okay. And that surface current exactly would be the difference between these two magnetic fields. Okay, so hopefully that makes somewhat intuitive sense. All right. So we can also derive boundary conditions for the D and B field, which is a little simpler. So you have the divergence of B 0. You apply volume integral on both sides. You already have on the right hand side 0, which means that now you can use the divergence theorem over the closed surface, gives you B dot ds equal to 0. And again, you take delta L to 0, and that will give you n hat dot B1 minus B2 equal to 0, right? Because now you have the divergence theorem and the volumetric Stokes theorem. So this is saying again the normal component B across a boundary between here and here, it's a different color, has to be equal. Okay. And again, similarly, we have volume integral of divergence of D. There is nothing but the volume integral rho dV. And again, rho can become singular at the surface. So you end up with n hat dot d1 minus d2 is the surface current density, surface charge density, my bad. Which means if there are some charges on the surface that are embedded, net charge, remember this is always net charge, then essentially D can be discontinuous, the normal component. Okay. So one thing I should mention is that imposing E And H boundary conditions automatically ensures the D and B boundary conditions. And I'm not going to prove this because it's one of the homework problems that I've assigned. It's in the book as well as one of the book problems after chapter 1 in the textbook. But essentially, you can do it in a single coordinate system. I won't say more than that here. You can try it as one of the problems. Okay, so that's about the 4 boundary conditions which we've derived now. So one last thing I can say is that we'll do this more rigorously later, but I just want to mention it because we are discussing boundary conditions, is that in a perfect electric conductor, which is called PEC, right? The time varying field quantities all go to 0. So the E, H, D, and B fields all go to 0. In fact, even in static case, the electric field goes to 0. Only static magnetic fields can be inside a metal, right? And perfect electric conductor is nothing but a perfect metal. So why do the field quantities go to 0? Hopefully you've maybe seen that if you've taken electromagnetics before, but in intuitive reasoning, we'll make the reasoning more rigorous in the next lecture when we discuss materials. But intuitively, essentially, if you have an electric field that's non-zero inside a metal, then electrons inside the metal will move to make it 0. And they'll keep moving until it goes to 0, until the field goes to 0, right? And that's the idea. Um, and in a perfect electric conductor, we assume basically that these electrons move instantaneously and they don't have any delay. Or at least at steady state, you can say that there would be no fields, right? Because they react instantaneously. And the same goes for time varying magnetic fields, because when you have a time varying magnetic field, that generates a time varying electric field as well. So all field quantities must go to 0. And that's what a Faraday cage essentially does, right? Is that doesn't allow fields to penetrate through it. Okay, we'll discuss that more rigorously in the next lecture and see where the field quantity E, and H going to 0 comes from. So if that's true, then n hat cross E1 minus E2 is equal to 0 implies, and in material 2, if I call that to be a metal or a PEC, then on the surface of the metal, it says that the tangential component of the electric field must go to 0, right? Mm. Magnetic field on the surface is given directly by the surface currents. And these are currents that are flowing on the surface of the metal, right? So in metals, the currents and charges all accumulate on the surface because, of course, on the surface, they don't have anywhere to go, right? They can only move along the surface. Uh, Whereas from inside the metal, they can be moved out. So E equal to 0 in metal B, rho S. So these are the boundary conditions for a PEC. Okay, so that's about boundary conditions. They're very useful. We'll see them over and over and over again. So it's good to kind of get some intuition as to what they're saying and understand them well. Okay, so let's move on to constitutive relations, sometimes called wave-matter interactions. So far we've only defined the fields, the E, H, D, and B fields, and they are of course related through Maxwell's equations, but the fields are also related through material properties. So depending on what kind of material you have, the D is related to E and H, and the B is also related to E and H in specific ways. And those ways are kind of defined by, those relationships are defined by what are known as constitutive relations. All right, so in general, the most general form of these constitutive relations can be written as t is a function of nh, some fd function of nh, and b is also a function of nh, which I call as fb, b comma h. Okay, so this fd and fb are some functions, and these functions are determined by what kind of material you're dealing with. So today we'll just classify the different ways that these functions can show up. And in the next lecture, we'll look at the derivation of what exactly those functions look like, right? And we'll develop a model for those functions. Okay, so first we will start by assuming simpler case, let me say. Assume fd and fb are linear functions. Okay, so linear has a specific meaning. For example, f of x equal to x, that's a linear function. F of x equal to x squared is also a linear function. And it's an interesting question. F of x equal to x plus 1, is this a linear function? Let you think about that. Okay, so what's the definition of linear? If I have x comma y, or not x comma y, sorry. I have a function f of x defined as I have some function f of x, then f of ax plus by is f of ax, a of f of x plus b f of y. So you can apply superposition essentially, is that's what it means. Okay, so we'll assume that these functions are linear, and that makes the mathematics way simpler to deal with. Otherwise, it gets very complicated. A lot of tools that we have in mathematics are, they all assume that the functions you deal with are typically linear. If you don't have superposition, you don't have a lot of things, actually. So this is a good assumption to start with. Later on, maybe we'll look at, what happens when you have nonlinearity as well. But for now, let's assume it's linear. These functions are linear. Okay. So case one, it's the simplest case, which is free space. Okay, so in free space, D is epsilon naught E, and B is mu naught H. So those are how they're related. And maybe you've seen this before. Epsilon naught is called the permittivity of free space, which is about 8.85 times 10 to the minus 12 farad per meter. The mu naught is the permeability of free space, which is 4 pi into 10 to the minus 7. So these quantities were derived empirically through experiments. So yeah, that's what they are in free space. There are ways to interpret them, which I'm not very comfortable with, and I'm not going to mention them, but just say that in this case, okay, this is how they are related. The interpretation is, I would say, more reasonable when you have actually a medium there rather than free space. But maybe one way to interpret epsilon naught and mu naught is the amount of electric and magnetic energy stored per unit area, per unit volume of space. And we'll see that when we do power transfer and flow of power, is that in fact they do represent some kind of capacity to store electric and magnetic fields in space. Okay, so the next case is the next simplest case, which is isotropic and homogeneous. So what does isotropic mean? So isotropic means that the material properties are not a function of the electric field direction. So the material properties are independent of the vector direction of E and H. Right? Which means what? Which means that if the electric field is pointed this way or it's oscillating back and forth like this, we haven't really described the oscillation and stuff, but forget about oscillation. Maybe I'll just say the direction, right? We know that the electric field is a vector. So if it's pointing this way, the material has the same properties as if it was pointing this way. So that's what isotropic intuitively means. And homogeneous means that the properties are independent of space or position vectors. Right? So it's essentially like a uniform mean. Everywhere it's the same material properties. Okay, so space in fact is isotropic and homogeneous because it doesn't really have any material anywhere. But of course, you can have the same material everywhere, then it would be homogeneous. And if it's the same no matter the orientation, so if I kind of rotate the coordinate system, or if I rotate the fields, the field vectors, it doesn't change. So in that case, then the D and E are related as just a single constant. Epsilon E, which is some constant epsilon R times epsilon naught E. And we'll see what this epsilon R is. Similarly, B is mu H, which is a constant epsilon R, mu naught H. Okay, so epsilon R is called the relative permittivity. Permittivity, there's two T's. Mu R is the relative permeability, the medium. So sometimes the relative permittivity is also called the dielectric constant. Okay. All right. So what is this epsilon R and epsilon mu R, right? So where do they come from? So here we'll kind of focus more on the intuition, and in the next video we'll derive a rigorous model for it. Right, so what is really going on? So you have some medium. It's made up of, let's say, some kind of atoms or molecules. I'm just going to draw it like that in some kind of a structure, right? Doesn't matter what medium it is. So we can assume for the simplest case that this atom or molecule has some electron cloud, let's say. Of course, these get very complicated, but we're taking a very simple model here. And there's some kind of nucleus, or you can think of it as just some positive charge, right? So in a neutral atom, this is not always true, but let's assume that in a neutral atom, the center of positive charge and the center of the negative charge are the same, which means that this does not have any dipole moment. Right? So dipole moment is if I have a positive charge and a negative charge that are separated by some distance delta L, then the dipole moment is given by Q delta L vector, where delta L vector goes from the negative charge to the positive charge. Right? Okay, so an atom that's like that, or a molecule, or some kind of a unit, let's say, that does not have any dipole moment, is when the electric and with the negative charge and the positive charge have the same center of charge, right? Okay, so now if you have this kind of a thing, let's just say atom, and I apply an electric field this way. So this is the electric field. So then what happens? What happens is that these electrons or this negative charge is pulled in this direction, right? And this positive charge is pulled in this direction. And because electric field goes from, let's say, some positive charge, some positive to negative potential, right? Okay, so what happens to this atom then? Gets stretched out or deformed, right? So now my electrons or my positive charge is somewhere down here, and the center of my negative charge may be somewhere up here, right? Again, this is just a very simple, simplistic model. But we'll actually say that it's a very accurate model for most materials, for many materials. Okay, so now I have a dipole moment that's created. I can call this to be plus Q, this to be minus Q, and there is a dipole moment in the same direction as the applied electric field. This is the applied electric field. So maybe I'll call this E0, which is the original applied electric field. And now you have a slightly modified applied electric field because each of these atoms also has an electric field associated with it that's flowing this way. So this is, let's say, a static field. This should be in this direction, right, from the positive charge to the negative charge. And that actually reduces the applied electric field E0 by a small amount. Right? So this E, in fact, is less than E0. Okay? So we said we have this dipole moment, P, which is Q delta L. It's a small p, not large p. Small p. I don't know if that's a small p. That's small p. Okay. And if I have n elements or n of these units per unit volume, or n of these atoms per unit volume, then I get something called the large P, which is the polarization vector in Q delta L. This is again a definition. Polarization vector of this medium. Okay. And an empirical result is that when this applied electric field is weak or relatively weak, then this polarization vector is proportional to the resulting electric field, which is this E, right? The final electric field, once everything has settled down. It is proportional to that. Okay, so that's an empirical result. That's not always true, and that's where the nonlinearity can come in these materials. We're not going to discuss that here, but if it's a small, if the applied electric field is relatively weak and not too crazy, then they do have a linear relationship, and that is given by epsilon naught chi E of E. Okay, and this epsilon naught is kind of put in there, but chi E is the constant. It's a constant. And this constant is called the electric susceptibility. So it's a nice name because it describes how susceptible is the molecule or the material to get polarized. Right? If the susceptibility is high, then for an applied electric field E or for an electric field E, you have a much higher dipole moment per unit volume, P. Right? So this is actually nothing but the dipole moment per unit volume, the electric dipole moment per unit volume. Okay, this is, let's say, number of atoms or units per unit volume. All right. Okay, so now that we have this, the D field is given by epsilon naught E plus this additional polarization vector in the medium. Okay. Which is nothing but epsilon naught E plus epsilon naught chi E, which is epsilon naught 1 plus chi E, which is, of course, epsilon naught epsilon R E. So which means that epsilon r is 1 plus chi. So that's the relationship. Okay. So typically, chi e is greater than 0. And because, of course, if you think about it, when you apply an electric field, the electron does want to move in the same direction as, or in the opposite direction to the applied electric field. And this positive charge wants to move in the direction of the electric field, right? Because it's attracted to this positive charge up here. And that's the reason that the polarization vector in the same direction, which means that chi is greater than 0, right? Now, for chi to be less than 0, that would have to mean that when I apply an electric field, the electron wants to move in the direction of the electric field and the positive charge wants to go up. That doesn't really make sense, right? Why would electron go towards negative charge? Which means that epsilon r is greater than 1, right? But there's a big but here. But this assumes that material response is instantaneous. So what does that mean? That means that as soon as I apply the electric field, instantaneously the electron and proton have kind of gotten separated, right? But in reality, we know that's not true because the electron and the positive charge of proton, if you like, they have some kind of inertia, right? So when I apply the electric field, the electron and proton take some time to separate out, right? So it takes some time for that polarization vector to develop. Now you can imagine that if I apply an electric field, let's say I apply it this way, okay, and after 1 second, finally, they have been separated. So let's say it took 1 second, just as an example, for this electron to go up here and the positive charge to come up here. But within that 1 second, by the time before they even got a chance to respond, if I flip this electric field this way, now, so it got flipped. So this electric field is oscillating so fast that the delay in response makes it look like when the electric field has flipped, this electron and proton are still out here, which means now it looks like the electric field is flipped and the electron has gone in the direction of the electric field, right? So that would make it look like chi in fact is negative because at this instance, at this point in time, the electron or proton are in the opposite direction, or they are not aligned with the electric field, right? So this polarization vector now is this direction, whereas the applied electric field has already flipped to this direction. So this looks like as if chi is negative, right? And that's actually what happens. And we'll see that when you have time varying electric fields and you have a delay in the response of these particles, you can have chi look like it's less than 0, right? In reality, I can be less than 0. Let me say chi can be engineered or can look like it is negative. Okay. That's really the basis behind from where that can have very serious implications actually, and we'll see. And these materials that are engineered to behave this way are called metamaterials. So this is where metamaterials originally came from. I mean, today, of course, it means something more general, and it's used in a more general way to mean essentially periodic structures. But originally, metamaterials, I guess, came from the study of these material properties that don't follow, uh, I guess, norms in some sense, right? So typically you expect epsilon to be greater than 1 or epsilon r to be greater than 1, but you can make epsilon r less than 1 or even less than 0. when you design them or engineer them to behave in these weird ways. These are called metamaterials. We'll look at them more later in the class, but that's just kind of an introduction. Okay, so in an analogous fashion, for magnetic fields, you have B equal to mu H, which can be written as mu R, mu 0 H, which can be written as mu 0, 1 plus chi m H, where this chi m is the magnetic susceptibility. Which is nothing but mu naught H plus mu naught chi m H. And this is the magnetization vector M. Magnetization vector. And that's the dipole, the magnetic dipole moment per unit volume. Um, when it comes to magnetism, it's not so easy to develop such an intuitive picture, and the models when it comes to magnetism are much more complicated. We're not going to treat them in this series. You would really study them from quantum mechanics if you take a class on, or if you watch lectures on condensed matter physics or solid state physics, where they do deal with these magnetic phenomena from quantum mechanics. But it's kind of beyond the scope of this class. But we'll just kind of quickly classify them. And at mu r is usually greater than 1. You have paramagnetism. And this is something similar to what we had earlier, the electric case. It's a very weak phenomenon and it's typically not permanent. Right, so these magnetic dipole moments basically line up with the applied magnetic field, and you can get this kind of an effect. And then you can also actually have mu less than 1 in natural materials. That's called diamagnetism. Again, it's kind of a weird phenomenon because it repels stuff. Right, so there's an interesting experiment for levitating frog on YouTube. So they made a frog levitate because water, in fact, is a diamagnetic material. Most materials actually have some form of, most everyday materials like water and some metals have a very weak diamagnetism associated with them. So diamagnetism is basically when the polarization vectors are in the opposite direction, or the magnetization vectors in the opposite direction of the applied magnetic field. Right? So it's a very weak phenomenon. And since the frog is basically water, um, this repulsive effect coming from diamagnetism could be used to levitate it. But you need very strong magnetic fields to do that. Okay, so material is typically repelled by permanent magnets. Okay, then the third one is R is much greater than 1. That's called ferromagnetism. And this is your typical fridge magnet. Right, so this is an interesting phenomenon. It's a very strong effect. Okay, and it's typically a nonlinear effect as well. So it's associated with nonlinearity and hysteresis, which means you can magnetize this material and you remove the applied magnetic field, but it doesn't go back to zero. These dipole or magnetic dipole moments that are generated can remain in the material. And maybe I'll say one thing, which is that essentially you have these strong domains inside of dipole moments or magnetic dipole moments that are all lined up, and it's a very strong effect. So this is how your permanent magnets are made. Maybe I'll just write down that these subdomains. There's also a ferroelectricity, ferroelectricity. It's the same idea where you have um, an electric dipole moment embedded already in the medium, in the crystal structure or in the atomic structure. And you can again get similar effects. So it's very popular actually now, ferroelectric materials in research. But this is really not a materials class, so I don't want to go too much into that. We'll kind of look at these phenomena at a macroscopic level from the point of view of epsilon and mu, rather than looking at the molecular level. Uh, okay, so the other phenomena as well, there is antiferromagnetism, where these dipole moments actually line up in opposite directions pairwise. And there's ferrimagnetism, where again you have pairwise, but they're not exactly the same size. And there are other phenomena, superparamagnetism, there is ferroelectricity, as I said. And this is for both E and M. So you have antiferroelectricity, antiferromagnetism, ferrielectricity, ferrimagnetism, and so on and so forth. So there are many complicated phenomena because you can have all these complicated atomic structures that interact in very complicated ways, right? So this is kind of where we'll depart from the discussion at the molecular stage. We're not going to do that. We will develop in the next class a very simple model, though, of this phenomena here, right? This kind of um, applied electric field and then the dipole moments forming. Okay, so that's about case 2. Let's move on now. It's quite an aside, but I think it's kind of important to know that a little bit. Case 3 is inhomogeneous medium, where it's a function of space essentially. So the D field is a function of space. Sorry, not the D field. The permittivity is a function of space, and the permeability is also a function of space. So you need to be careful when you have something like this when applying Maxwell's equations, because divergence of D is equal to rho, which means the divergence of epsilon E equal to rho. You can't take this epsilon outside now, right? Because you have a divergence of two quantities that are functions of space. So you have to apply a vector identity here. So this is not equal to epsilon times the divergence of E equal to rho. So you can't actually write divergence of E is rho over epsilon here. Right, so makes things a little bit more complicated, and we'll do some cases of actually we'll treat wave equation, things like that sometimes under this inhomogeneous condition. In fact, in HFSS, they do use the inhomogeneity of different dielectric media. So they do solve a vector wave equation there, which does not assume homogeneous medium, right? Because usually you don't have homogeneous medium. You have, let's say, a PCB with different layers, and each layer is different. So you need to treat it carefully. Okay. Case 4. So we're making it slightly more and more complicated with each case. Is anisotropic, which means it's not isotropic. So what does that look like? Right, that looks basically, if you go back to the atomic picture again, you have an applied electric field this way, but the polarization vector forms maybe in this direction. And that could be because the positive and negative charges, it's negative to positive, the positive and negative charges are constrained in some way because of the crystal lattice. Right, so that because of that, maybe they cannot move in the same direction as the electric field, and they can only move in some defined planes. Right, and that's where you can get this polarization vector to be not aligned with E. Then what happens? So we know that D is epsilon naught E P, right? So what does that mean? That means that you have an electric field in this direction. Let's say this epsilon naught E. Now, polarization vector, maybe it is in this direction, E. And you have to take the sum of these two, which means the D field is here. Right? So in general, in an anisotropic medium, the D and E field are not in the same direction. They actually are in different directions. Okay? So how do you relate them? So if you have two vectors, D and E, that are in different directions, how do you relate them? So using a dash, right? So if I have two vectors and I want to form a relationship between them that is linear, then I need to use a linear transformation, right? And linear transformation in some basis can be represented as a matrix. So if you've taken a linear algebra class, you've seen what a matrix is before. Uh, of course, linear algebra today is so popular, right? So hopefully you've seen it before. So which means that the D and E field are related by a matrix, which is sometimes called a tensor. Tensor is just a fancy word for a matrix. Okay, so this epsilon matrix can be written as epsilon naught xx xy z yx y y yz. There are obviously 9 components to this matrix because the D and E fields are three-dimensional vectors zy zz. Okay. Suppose in general, if it's not only isotropic but also inhomogeneous, then these can be position dependent, right? Okay. And if this epsilon r, so I can call this whole thing as an epsilon r matrix, right? Because I put the epsilon naught outside. So epsilon r, there are special cases which we'll define. 0, 0. So if I only have diagonal elements, that is called a biaxial medium. And if I have diagonal elements of which only there are two unique ones, so let's say Ex and Ey are equal, or let's say Ex, Ex, Ez, and then zeros everywhere else. This is called a uniaxial medium. So we'll deal with this when we get to plane waves. We'll see what happens to plane wave when you have a uniaxial medium. Okay, so these are very interesting because, in research, it's really this stuff that people don't really look at as often, right? Because the mathematics becomes very complicated. But you can get very interesting and useful properties out of these strange materials. And that's kind of the philosophy behind metamaterials, right? In some way, is that you can get strange behavior from media. Okay, so case 5, which is probably the last case we'll do today, is bi-anisotropic media. So this is the most general case in the linear response domain, where the D field is a function of both E and H, and it's related by tensor quantities to both. E plus mu tensor H. Okay. So this is the zeta. So symbol is zeta. And sometimes called the magnetoelectric tensor or the magnetic electric tensor. And this is psi or xi, yes. It's called the electric magnetic or electromagnetic tensor. Okay. All right. So there are special cases also of bianisotropic media, chiral media, the intelligence media, and so on and so forth, which we may look at later, where they satisfy certain constraints, which makes it a little bit easier to analyze. But bianisotropic media actually are quite popular in research in some areas where you want to look at some special behavior of how wave propagates through these media. And then we may look at some of that during the class. So maybe this is a good point to stop. We have just do a quick review. So in the last class, we looked at Maxwell's equations, and in today's class, we looked at boundary conditions. So we derived boundary conditions for the E and H fields, and the D and B fields at an abrupt junction between two media. And we said that, okay, in case of a metal, they satisfy these nice relations where the tangential electric field is zero, tangential magnetic field is directly related to the current that's flowing on the surface. And we said that the B and D field boundary conditions don't need to be explicitly imposed if you impose the E and H, which we did not prove, but it's part of the homework, I guess. And then we went on to wave matter interactions. We defined 5 different cases of how the D and B fields emerge from the E and H fields. Starting from the simplest case and then moving on to slightly more complicated cases. And then we developed sort of an intuitive picture of where epsilon r and mu r come from. In the next video, we will look at the models to develop what exactly this chi looks like. Here we just kind of defined it. Right? So how is it a function of frequency? What does it actually look like? What does it represent? So we painted an intuitive picture here. Mostly it was just definitions. In the next class, we'll look at deriving the model itself. Classified some of these epsilon r and mu r into different types of materials under the homogeneous case. And then we did inhomogeneous and isotropic media. And in the end, we said, okay, the most general form is in fact a bianisotropic inhomogeneous medium where you have 4 tensor quantities, which can also vary as a function of space. Okay, so this is sort of very complicated. We may not deal with bianisotropic media that much in this class, but it's important to kind of know that something like that exists. Okay, so this is a good place to stop. Hopefully things were clear. If you have any questions, you can leave them in the comments below and I will try to answer them. If not, thank you so much. I'll see you in the next one.